Hello everyone. Today, welcome back to this video of Math for Quantum. So today I would like to explain a little bit um, about fundamental effect in quantum mechanics, which is called entanglement. And this is something that alongside with superposition that we saw last time in the video of the double slit experiment. It's at the heart of quantum mechanics, and it differentiates a lot between uh, classical mechanics and quantum mechanics. Most of the intriguing and fascinating effects that we can exploit eventually with quantum mechanics are due to superposition, entangling, and tunneling, uh, which which is something that I will discuss in another video. Tunneling, for example, at the base of nuclear decay or other interesting effects. But okay, so let's forget about tunneling for a moment. We will make a dedicated video for that. But superposition, we know, we have an idea what is a superposition. So we have a state, psi, which is whatever we can say and we can assess about a particle, in this case a single particle. And to make my life easy, today I will be talking about just one particle with two dimensions, with two possible outcome. So um, 0 and 1, 0 and 1, and this particle can be in these two states. 0 and 1 are the labels, are just numbers that we put for to to indicate the velocity, for example, of that particle. So v1 will be related to the number 0, and v2 will be related to the number 1. I'm kind of cheating here because usually velocity is not a binary value. Velocity spans over a range of number, and it's a continuous number in the real domain. But just to, I don't want to talk about spin right now. I will do a dedicated video for spin in the future. Spin is a um, perfectly binary um, system, so it's spin up or spin down. But I don't want to complicate the physics at the moment. I would like just to talk about the math behind entanglement, and for that I just need two values. So suppose your system can be found in only two possible velocity, for whatever reason. We simplify in this case, okay? Doesn't matter if we have an example in our head. I just want to have the possibility to write it in two states. It can be either 1 or 0, and the superposition, as we all remember, is that state that is called 1 plus 0, which is a complex number, so it's not the real number. We don't have the probability yet, and this is the state at which we found the state when it's propagating. So when we are not observing, when we don't look, when we don't do measurement on it, we have a state that is undetermined, because you see that it could be either 0 or 1. We don't know what it is. If you like, in a vector space of complex, the complex plane is exactly this vector here, 45 degree between 0 and 1. We can write it this way if you like. Um, we stick an I there, but it doesn't matter. We can put an I if we want. The concept is the same. We have two possibility, and the superposition is happening in, let's say, in the quantum world, where we let the system evolve. It doesn't interact, it doesn't collapse. And then we all know that there is, as we said in the double slit experiment, there is the collapse of the wave function, of wave function, and and the collapse is whatever measurement or whatever interaction leads to the state um, to be falling in one of the two possibilities, either 0 or 1. So when and this is happen in the real world, because when we do a measurement, then we get the value 0 and the state in velocity 0, and we can see that the velocity is 0. Or we state the velocity, we get the value 1 in our apparatus, and then we say that the velocity is v1. Classical physics usually happens when the decoherence with this plus is gone. So when this state collapses, we see the effect of the remaining of the state, the average of the state, and it's after the collapse we get whatever classical effect we see in real life. But we know that superposition do have effect, because we had the video on double slit experiment and we can see the fringes interference, and there are so many others examples in which the superposition has a role. So why I'm talking again about superposition? Because to talk about entanglement, you kind of need to have superposition in your bag. So entanglement is, first of all, what is entanglement? So it's a kind of superposition, but the first thing that uh, we need to deal with is you cannot have entanglement with only one particle. Okay, so we have particle 1 and particle 2, P1 and P2, and then you can talk about entanglement. So at least I'm being strict here. There are some cases in which we can talk about hyperentanglement when we use not many particles but many degrees of freedom. But I want to be strict and study the case where how it's born basically, and the idea is to have two particles which are described by two-wave function, psi1 and psi2. And the entanglement, and of course psi1 is can be either 0 or 1, or a superposition for what matters. And this is important to allow us the possibility to have the superposition, and as we will see soon. And psi2 is the same, could be, but let's pick a different color, 0 and 1, or could be plus or even minus if you want. It doesn't matter which superposition you pick, it could be any superposition. Okay, and we will deal with this one at the moment. I keep forgetting the factor of 2 here. They need to be normalized in order to have the probability 1 at the end, and we know that, but that's okay. So we have two particles, and what happens to these two particles? So entanglement is when you cannot describe the state of two particles as if they were composed by two correlated single elements. This is a bit of a buzzword to say that they behave in such a way that it's impossible to basically disentanglement, basically. So to treat them as a separate basis. The joint description is as if they were of a single wave function psi, big psi, let's say, which is described by, for example, the 0 in particle 1 and 1 in particle 2. This is a possibility. Plus, and this is the important thing, there is a superposition of one of the other case scenario, which is in divided square root of 2. Okay, so the red one is particle 1. Now I should write it in red. And the green one is particle 2. And the entanglement is the superposition of the two states, this infinity. I draw it as an infinity to just to say that there is nothing to deal with infinity. It's just they are intertwined, they are interlinked. You cannot look them in a single way without disturbing the other the other state. So they are, in a sense, one whole thing divided into subsystems that they are interlaced to each other in a way that is very subtle. Because um, basically you can do a we can do a game to try to understand what is this entanglement. So having in mind that is a superposition, so um, of two states, and the joint description is this one, which I will rewrite up here for psi big, and this is 0 and 1 plus 1 and 0. So, but what does this mean physically? This means physically that um, if we can see that if we measure the particle 1 in state 0, we know for sure, and this is the case, we know for sure that particle 2 will be in state 1, because we can see that, right? Particle 1, okay, when it is in 0, particle 2 is in 1, but when particle 1 is in 1, particle 0 is in 0, okay? So in a way, we can see that this is a highly correlated system, which tell us that no matter what you do to no matter what you do to the system that you are looking at, the other one is, in a sense, instantaneously um, correspondent to the first one. You don't need to measure the second one to know that it will be the same state as all over the time one. You just need to look at the first one to know that the second one is whatever you have in this correspondence. By the way, you can have a different entangled state where the system are correlated 0, 0 plus 1, 1, meaning that no matter whenever you measure 0 in one state, you will have 0 in the other one, and whenever you will measure 1, you will have um, 1 in the other state. These are correlated instead of these are anti-correlated, if you like. 0 and 1, 0 in the basis, in the logical basis, and this is correlated. Okay, so so far you can you can think that this is something that can happen in classical mechanics as well. If you think about an example, for example, you have a box, and then in the box you put two objects, one red and one green. When you open and then you separate the box in two places, you know that one box will have the red one and the other will be green. And this is a kind of correlation that is inside. What you cannot get in classical mechanics is that suppose you have a box with more particles, suppose two green and two red, you cannot um, you cannot assure that when you divide the particle in two separate places, they would be always correlated. In fact, in a classical system, when you will draw one whatever color you will draw here, you can get any combination. You can get red and green, or green and green, or green and or red and red, and green and red. Okay, and this is because um, classical objects do not allow for the superposition of exclusive states. These are exclusive. So if it happen once, it cannot happen the other. And this is, if you want, we can make another example that try to should be able to um, think and to understand, grasp this correlation of distance. By the way, there is no physical. So the other thing that you can think is that when you measure one, the other is instantaneously changed into the correspective state. But that cannot be possible because it's been proven and already that there is no, even if you separate the particle in two distance location, and this is 0, can think that, okay, maybe the particle sends a message to particle 1, particle 2 to make it 1, or 0, the other way around. But this message cannot be sent because it has been proven that this correlation beats the speed of light. So it's there even though the two particles are separated by a distance that cannot be reached by any signal instantaneously, basically. So this means that this correlation cannot be explained with a underlying classical physics or a mechanism that is hidden, and it's explaining this correlation. So suppose you have something that you cannot know, but it's hidden in the physics. And there is a Bell, it's called Bell theorem, Nobel Prize, that assure us that there is no communication between the two parties. So in a sense, you cannot explain this strong correlation with some signaling between the two systems. And actually, this is also the reason why you cannot send communication with this entangled state. But you can do other interesting things like computing or secure cryptography. Maybe I will do a video on the application next. But let me conclude this video with an example. Suppose you have a coin which is flipping, and when it's flipping between zeros and one. Okay, so the coin is spinning around the axis, and you can think that the coin that is spinning between zeros and one is very much like the superposition of a qubit 0 plus 1. What's the difference between a coin spinning and the superposition 0 plus 1? When it's spinning, you don't know if it's 0 or 1 unless you block it, and it will collapse in either 0 or 1 when it stops spinning. So when it's spinning, it's kind of like a superposition, and when it stops spinning, it's like the collapse of the wave function. Okay, but of course a coin is not a qubit. So what's the difference? The difference is that a coin, you can take an observer, an eye, for example, that is looking at the coin with a camera, and if the camera is quick enough, you can instantaneously check if the coin is in whatever orientation, 0 or 1. This cannot happen in quantum mechanics. In quantum mechanics, as soon as you put an observer that looks at the system, you will not know which one of the two outcomes you will receive, and you will get with 50% probability, in this case because it's a square root of 2 down here, you will get either 0 or 1. So you cannot trace the trajectory of your coin spinning, but you can do it with a high-speed camera. So this analogy breaks down of the coin in the superposition when you use the right tool. But it's good to have in mind this spinning coin for the entanglement, because suppose now, to give you an idea of how entanglement works and how it's puzzling, and the power of entanglement is, suppose you have two spinning coins. The analog that this entanglement does is that you have a two spinning coin, one is 0 spinning, okay, so we don't know what is 0 or 1 because it's spinning, and the other coin is here and it's spinning as well. We write 0, 1 to say that we don't know what it is. Okay, and they're spinning and they're in two different positions. Now, they can be 100 kilometers away, it doesn't matter. It can be a galaxy away, we don't know, but let's put 100 kilometers, they're still spinning. Of course, if you think about a real coin, whenever you stop spinning one of the two by clapping on it or stomping on the table, whatever, you will get 0 or 1, 0 or 1. And then you do the other one at 100 kilometers away and you will have 0, 1. But those two things will not talk to each other, so you can get the four possible combination. You can get 0 with 0, 1 with 1, or you can get 0 with 1 and 1 with 0. You can get four possibilities. And this is a classical It's better. You can do it on a table. You can spin two coins. You do it 100 times, and you will see that you will get with 50% um, probability the four combinations 0, 0, 0, 1, 1, 0, 1, 1. Okay, these are all the possible combinations that you will get with 50% if the coins, of course, are balanced and not tricked. But what happens with entanglement, which is weird, so let's say that this is a qubit now, and to say that this is a qubit, we put a Q, so a spinning coin like a qubit. What happens is that um, you will have only either 0, 0, 1, 1, so always correlated, so with 50% actually, so you neglect these two, or you will have the other two depending on the state that you prepared in the entanglement, or you will have the 0, 1, 1, 0 and not the other two. So as you see, you're doing something with 50% actually, not 25% of four combination, but 50% only two combination. So in a sense, this is an amazing uh, fact that even if you break the system apart in very distant location, it still behave as if it were a single system 0, 1 or a single system 1, 0. The last subtleties that I want to say is that you can think, okay, maybe there is something in the coin that allows you to basically change the state of the system in a superposition of 0 plus 1, and this will make your system not entangled, because maybe you're looking in a particular way, and then there is something in the 0, 1 state that is special about it. But that's not the case, because you can also change the base. So you can make your system 0, 0 plus 1 over square root of 2, and your system 1 make it in 0 minus 1 square root of 2. And this can be done with a simple matrix 1, 1, 1 minus 1, which is a transformation that you can do on your physical qubit. No matter what qubit you use, it could be a photon, it could be a resonant qubit, it could be an atom. There is always the possibility to create the superposition from the single state. This is experimental fact. We can do it with light. I will do a video on polarization, but believe me, you can do that. And we call this superposition state. We call them plus and minus. Okay, plus and minus because of the relative phase. One is minus and the other is plus. Okay, so you can do the transformation on your state, on your psi, big psi, and then you will have plus plus. I think plus minus minus. We can do the calculation. So 0 plus 1 plus 0 minus 1 plus 0 minus 1, 0 plus 1. And actually this is 0, 0 minus 1, 1 plus actually minus 0, 1 plus 1, 0, and this is plus 0, 0 minus 1, 1, 0 plus 1 minus 1 plus 0. And then we can see that this is 0 minus, I'm doing some calculation here just to minus 1 plus, and then we get 0 right, so 0, yeah, so 0, 0 plus minus 1 plus, and so this is plus, yes, plus with, there is a minus, okay, plus with minus, minus, I think it's in the other way around, but it doesn't matter. I didn't want to do the calculation now. You need to collect the correct terms, but you can get basically either this one or one of the other ones, depending on the phase. So it could be this state, minus plus. It could be this state here with a minus, or it could be this state here with a minus inside. It doesn't matter which one you get with the transformation. The important thing is that still it will be still over square root of 2. It will be still correlated in pluses and minuses. You see, plus will go with minus, minus will go with plus, etc., etc. So, um, and this game will be the same if you measure the state plus instead the state of 0 and 1. So you will get, instead of zeros and ones, you will get pluses and minuses, which is just a different observable. Instead of looking at the velocity, you look for example, the sum of the velocity and the difference of the velocity. So the analog would be, instead of looking v1 and v2, which are zeros and 1, you can get at the v1 plus v2 and v2 minus v1, which give the same information, just in a different basis, in a different, if you want, way of looking at the system. So what I'm saying is that there is no way that you can disentangle this state easily. You need to do complicated uh, things to disentangle actually something that is entangled. And actually this is also the power of entanglement, because the entanglement allows you to unlock, as I said, powerful computing, and as I will try to show you in the next videos, and secure communication, like QKT. It's called QKT. Okay, so I hope that you you get something out of this entanglement video. So as you remember, just as a recap, you have two bodies, um, and then superposition, and then you have strong non-local, meaning that no matter how far apart, they are correlated. Correlation. So they, as if they were talking to each other by changing their state um, instantaneously, but there is no communication in between, because this can be shown, and this is prevented by uh, special relativity. So we know that nothing travels faster than that, not even the entanglement. Okay, so I hope you like the video. Follow me for more, and next will be on possibly polarization or quantum computing. I don't know, we'll see. But follow me for more on this channel. Thank you. Bye.